And we're back. Welcome back and happy Thursday. Today we will continue on with inference, give some examples of method of moments estimation, additional examples, and pivot to a second method of inference, so-called max likelihood or maximum likelihood estimation. But before we begin, some administrative bits. The reading on max likelihood, section 9.1.2, pages 242 to 245. It's not a lot, so please make sure you're keeping up with the reading. Homework number 3 concerning method of moments estimation is due Tuesday, the 30th, this coming Tuesday, at the usual 11:59:59 seconds, 1 second before the stroke of midnight. So why don't we continue? When we last left off, we talked about method of moments estimation, and we used the example of the Poisson distribution, and we said you equate the first population moment for the Poisson with the first sample moment for the Poisson distribution. You set up that equation and then solve for the unknown for our parameter lambda, which is the result of our expectation of x, which is the first population moment. And we write lambda-hat because that expression is going to be our estimator, that reasonable replacement for the unknown population parameter lambda. So why don't we continue with some examples? And we're going to go from beginning to end with this, which is more indicative of an actual data problem, just like the homework. So imagine then we have some measurements of the execution time for jobs, 30 of them, that are running on a processor. So let's look at some of these measurements. Now, of course, in Unix, there's a tool called top on the command line, and it'll show you the CPU time as well as the wall clock time associated with processes on your system. So you could absolutely produce a data set like this. There are 3 rows of 10 for a total of 30. So the first thing we would do is say, okay, well, we have this data set. I want to do inference with this data set, but I don't really know, ground truth, I think I know, but I don't really know what type of distribution governs the population that gave me these samples, from which I obtained these samples. And so the first thing I'm going to do is visualize my distribution. I'm going to visualize it in 2 ways, a frequency histogram on the left and a relative frequency histogram on the right. Relative frequency histogram is the frequency histogram where each one of the bin counts are normalized. And so when I look at this, I think, well, it looks like a normal distribution, and these things traffic in time, these measurements, but there are 30 of these measurements. Now, look at the shape. It's not quite Gaussian or normal distribution. It's not symmetric. It's skewed to one side. And this shape is very gamma-like. So let's assume that these CPU times, these 30 many samples, are well described by gamma distribution. And so let's recall what type of stochasticity or the structure of stochasticity associated with the gamma. Let's recall that from last semester. We said a gamma is a sequence of steps, alpha, many steps, are so-called algorithmic execution, and each step takes some amount of time, where that time is described by the exponential distribution. And so in this case, our alpha is the number of processes whose runtime that we measured, where the runtime, each one is governed by the exponential distribution. And so from last time, we know that any random variable that's distributed as a gamma distribution, that gamma distribution is governed by 2 parameters, alpha, the number of stages of execution, and we have lambda that is associated with the exponential that governs the time for each of those stages. And so we have the density function for the gamma distribution, f of x, and it's a density function because this gamma traffics in time, and time is uncountably infinite. So it is a continuous distribution, and therefore, when we talk about the probability, we talk about the density function. And so here we have our density, lambda to the alpha upon gamma of a times x to the alpha minus 1, e to the minus lambda x power for x greater than 0. And so here, when we computed the statistics, the summary statistics, the first moment and the second non-central moment for the population moments for the gamma, well, that first non-central moment is the expectation, and that second population non-central moment is the variance. So we're using the same notation we talked about last time. And so the first moment, mu1, is alpha upon lambda, and the second population non-central moment, variance, is alpha upon lambda squared. So that being the case, we know what the first two moments are for the population moments for the gamma distribution. So let's model this data set that we have, our 30 many process run times that we've measured, and we're going to model this as a multi-stage execution, so a gamma distribution. So this is a so-called two-parameter model because this gamma is defined by the two parameters, alpha, the number of stages, and lambda, governing this exponential, the time for each stage. So the first thing we're going to do is compute the first sample moment. We already know what the population moments are, but we have to compute the sample moments because we want to use method of moments estimation in order to compute a statistic that we're going to use as a replacement for our alpha and our lambda, the unknown population parameters for the gamma distribution. So the first thing we're going to do is compute the first sample moment, and then we're also going to compute the second central sample moment. So let's look at this. The k sample moment we know is m sub k. It's 1 upon n, the sum of xi to the k power. Second central sample moment for case 1 is m prime sub k, 1 upon n, the sum of all of the xi minus x bar quantity to the k power. And so if we have the first sample moment, well, that's m1, so it's just x bar, right? That's just 1 upon n, the sum of all the xi to the 1 power. That's x bar. And if we compute this x bar from our 30 many measurements, we get a value of m1, or x bar, is equal to 48.23. Now, the second central sample moment, we'll plug in, and we're going to take our x bar from the first sample moment and use that in computing the second central sample moment. So m2 prime is 679.71. Now, of course, this is the same as s squared, but not as s. S is unbiased and has that leading coefficient as 1 over n minus 1. Okay, and so we have our m2 prime, we have our m1, and so let's keep them up there and also add up top our first and second central moment for the population moments for the gamma. And now we're going to equate. We're going to have two systems of equations. We're going to equate the first population moment for the gamma with the first sample moment, and then we're going to equate the second central population moment for the gamma with the second central sample moment. So if we do that, well, we get this equation. So we have alpha upon lambda is equal to m1. That's our alpha upon lambda, that's mu1. And then the second equation, we have alpha upon lambda squared is equal to m2 prime. So we're just equating the first moment with the first moment for population and sample, second central moment with the second central moment for population and sample. So now that we do that, we're going to do a little bit of algebra. For the first equation up top, we're going to multiply both sides of equality by lambda and divide both sides of equality by lambda. So that gives us alpha upon m1 is equal to lambda. For the second equation, we're going to do similar manipulation. We're going to take our lambda and we're going to substitute in for lambda. We're going to substitute here for lambda in the lambda squared. We're going to substitute in alpha upon m1. So if I substitute in alpha upon m1 in the denominator here and I square that, I get an alpha squared and I get an m1 squared, and then I have that alpha that was there before. So this leads me to m1 squared alpha over alpha squared is equal to m2 prime. And so what I did here is I took this result from the first equation, substituted for lambda in the second equation, and I get this expression in the second equation. So now I do a little bit of algebra, and I want to isolate this alpha and that alpha. I have alpha upon alpha, so I'm going to do that division, and that's going to give me m1 squared over alpha, because alpha in the numerator, alpha in the denominator cancel, is equal to m2 prime. So then I multiply both sides of equality by alpha, divide both sides of equality by m2 prime, and it gives me this result for alpha, and that's going to be my estimator for alpha. So I call it alpha hat. And alpha hat is m1 squared over m2 prime, and this expression, each one of these terms, the numerator and the denominator, I can calculate over data, because these are sample moments. All right. So now that I have that, I have two expressions, one for lambda. So I rename this lambda hat, because that's my other expression. And I take this lambda, and I'm going to substitute for what this alpha is. So I'm going to take this alpha, and I'm going to substitute m1 squared over m2 prime, do a little bit of algebra, and I get an expression for lambda, and I call it lambda hat. Lambda hat is m1 over m2 prime. And that is a function over data, and it's going to be an estimator that I'm going to use as replacements for the gamma. So now for the gamma distribution, gamma, everywhere I had my alpha, I'm going to use, for this gamma distribution, I'm going to use m1 squared over m2 prime, and then instead of lambda, I'm going to use m1 over m2 prime. So this is my replacement for alpha, and this is my replacement for lambda. Okay, and so this is a complete example of method of moments estimation. We started out looking at the data, hypothesizing a distribution that mimics the stochasticity we see in the data. And then once we have that probabilistic model that we believe has produced this sample set, or governs the population from which we get the samples, we then take the population moments for the parameters. We have two parameters. We take the first two population moments, we set them equal to their respective sample moments, and then we solve for the parameters of the model of the distribution. Here it's alpha and lambda because it's a gamma. Because gamma has two parameters, alpha and lambda, we use the first two moments, first moment and the second. All right, so this is our result. We have our estimators then, lambda hat and alpha hat. And each of these can be computed from the data, that 30 many samples that we had on the first slide, which are the measurements of the runtime of processes on the CPU. And so now we have our results. We actually calculated M1 from the data, that was 48.23, and M2 prime from the data, that was 679.71. So now we can actually plug in, and now we have values for lambda hat and alpha hat. So now if we use a gamma in something like MATLAB, we set our alpha to 0.071. That's our alpha, our estimator, and we set our lambda to 3.4227, and that's going to be our lambda hat. So then if we were to sample from this gamma distribution to mimic the process runtimes given this original data set, we're going to use this particular gamma with these concrete values for the parameters. And these are estimators, our functions, our statistics, our functions over data. All right. So with method of moments estimation, first step we follow is to think long and hard about the problem that you have at hand. And once you've thought about that problem, think again. Think really, really hard. So then, once you've thought about it, you can visualize and analyze those visualizations and select a distribution whose model assumptions fit. Now, the gamma structure of stochasticity for the gamma, it matched this idea of having 30 processes, each one of which consisted of a runtime. Now, once you select a distribution whose model assumptions fit, then the other question is the shape of what you see when you do the analysis, the visualization, does that make sense? Because if it is symmetric, it's most likely not going to be a gamma, for example. So then, now, once you select a suitable distribution that matches both the model assumptions as well as the shape, you then take that distribution, you count the number of parameters that distribution has. The number of parameters k. If it's a Poisson, it's one parameter, k is 1. If it's a gamma, it's 2 parameters, k is equal to 2. So once you do that, then you compute the first k population moments for that distribution, and then you compute the first k sample moments, or so-called empirical moments in the literature sometimes, and then you equate the population moments with the empirical moments. So you equate the first population moment with the first sample moment, and then you equate the second population moment with the second sample moment. And then you solve for the unknown parameters, and these solutions are your estimators. And you'll know you have an estimator when that closed form for the estimator is defined over the data. Okay. And so yes, absolutely. The main takeaways, you match moments. And if you cannot solve for the desired parameter, then choose another moment. Maybe you need the central moment instead of the non-central moment. Okay. So let's move on to an alternative method of doing estimation of parameters, or parameter estimation, so-called max likelihood estimation. So we're going to build up to this and then get to a point and continue on in the next module. And so the setup corresponds to James Bond, the spy. And James Bond, Agent 007, he's retired from the British clandestine service. Not satisfied with his retirement, our international man of mystery has decided to open a shop, a coffee shop. He needs help with mathematical modeling in order to optimize his caffeinated concern for fiscal success. And so Mr. Bond, like any small proprietor of a small business, sole proprietor, he does a little bit of everything. He waits tables, he serves coffee, he's a barista, or baristor, I don't know what the name is, but he does a little bit of everything. Bussing tables, handing out menus, everything. But being a former member of the clandestine service, he's always watching. He sees everything in the coffee shop. And so, in a 15-minute interval, Mr. Bond sees a customer, one customer, at the bar of the coffee shop. So he observes one person who walked in. And then, in the next 15 minutes, Mr. Bond is doing his usual, a little of everything. He sees 3 people come into the coffee shop and sit at the bar. Mr. Bond is very observant. And some other instant in time, 15-minute interval, Mr. Bond, ever so observant, sees 4 people at the bar in the coffee shop. And so we have here observations of the occurrence of customers arriving at the bar, events, and these are over standard windows of time, 15 minutes each. So then we ask ourselves, what distribution best models this stochasticity? And this fits exactly with the Poisson configuration that we talked about last semester in stochastic computing. So you think it's Poisson, and we write out the Poisson distribution, x distributed as Poisson, and we know from this that the Poisson distribution is governed or parameterized by a single parameter, that parameter lambda. Lambda happens to be our rate parameter. And for different settings of lambda, we're going to get different Poisson distributions. If lambda equals 1, we get this distribution. Lambda equals 2, we get that. And then as we increase lambda, the distribution kind of mushes more and more to the center, becomes less right skewed. And you can see lambda equals 9, it almost looks symmetric, like a Gaussian distribution, like a normal. So we're pretty fairly convinced that it's a Poisson. And this Poisson has a single parameter, lambda, if we were doing method of moments. But alas, this is not method of moments. This is max likelihood. And so the question is, if we want to know what is that population governing this arrival of events, one person, 15-minute window, 3 people, 15-minute window, 4 people, what is this ground truth population distribution that we believe is a Poisson? Well, we don't really know what lambda to choose. So we're going to enterprise to estimate the notional best lambda through this new method, max likelihood estimation. So one of the strategies then is, if we're going to choose a lambda, well, why not choose the lambda that best describes the observations that you have? So what exactly does this best describes mean? Well, we have our Poisson distribution, and the Poisson traffics in counts, so it's countably infinite, and therefore it has a probability mass function, and there's its closed form, lambda to the x e to the minus lambda upon x factorial. And so we know with this mass function and each one of our observations, we can evaluate the probability of observing one customer given a rate parameter lambda. We can also compute the probability of observing 3 people given a rate parameter lambda. We can also, for each one of our observations, evaluate the probability of observing that number of observations, or in this case, the last observation, given parameter lambda. So this gives us some notion of this idea of best describes the data, but we have this unknown parameter, this lambda. So for each probability, each observation, we have a probability of that observation assuming a given lambda. For the first observation, x1, the second, the third, up to and including n many observations. So we can absolutely express this idea of probability or likelihood for each of these observations. Now, this idea of best describes the data, now we need to pull in this idea of a likelihood across the entire data set. And this, we need a parameter, a value for lambda, that leads to the largest likelihoods over all of our observations. And so this is the parameter lambda that leads to what's called the highest joint probability. Each one of these observations, they occur jointly, the first one, the second one, the third one, up to including the nth one. And now we want the probability that all of these n many observations are going to occur together with the highest likelihood associated with the set of n many observations. And so we're going to make an assumption that each one of these observations are so-called IID, independent. They don't influence one another, and identically distributed. They're from the same Poisson. Okay, that's very helpful, because after all, we said they have the same lambda, and lambda is unknown. And so we're going to, for independent events, we know that the joint probability is the product of the marginal individual probabilities. And so if we want to construct this joint likelihood, the probability of the co-occurring x1 observation through xn observations, we're going to express that as the super product, I goes from 1 to n, of the probability of each of the xi, the marginals. And so we're going to select the lambda that maximizes this product of the marginal likelihoods. Now, this is a little bit messy, going to be kind of difficult to solve, so we want to make life a little bit easier for ourselves. How are we going to do that? And so we have our individual observations, and we have the likelihood, which is the evaluation of the probability of each one of those observations given some parameter lambda, and lambda is a variable because we don't know what it should be. We're going to multiply them all together, and so whatever product of each of these, that's what the super product is doing for us, whatever value of lambda maximizes this product is going to be our best Poisson distribution. And so this is the product of probability of single observations, which are our marginals, And so now we're going to select the parameter lambda for the p of x that maximizes the product of the marginal likelihoods. Now, of course, we want to clean this up because it's a little bit messy to compute. So we want to transform this expression because we want to make it simpler for ourselves. Mathematicians like things simple. They don't like complex things. So we're going to transform it, but we're going to transform it not in any fashion. We're going to transform it using so-called monotonic transformation. And a monotonic transformation is a type of transformation that is so-called order preserving. Let's take the example that we have the number 1, 3, 7, and 12. If we were to look at the order of them, we say 1 is less than 3, 3 is less than 7, 7 is less than 12. If we were to ask which one is the biggest, well, we'd say it's right here. It's 12. Now, let's suppose this is our x value, and we're going to compute a function. Instead of x, we have f of x is equal to 2x. Well, to multiply something by 2, that's a monotonic transformation, and it preserves the ordering of these values relative to where they were before. And so if we have f of x is 2x, this first one becomes 2, the second one becomes 6, the third one becomes 14, and the last one is 24. And so if we ask the question, which position, the first position, second position, third position, or fourth position, which position is the maximum occurring in for f of x? Well, 2 is less than 6, 6 is less than 14, 14 is less than 24. It's still the fourth element, which is 24. And so these monotonic transformations are order preserving. And the importance of that is that if we transform an expression like this superproduct with a monotonic transformation, when we still try to find that lambda where it reaches its maximum, it's going to be the same position. So it's the same value that optimizes where this expression reaches its maximum. And so that's why monotonic transformations are particularly important. You can clean up the expression, making it more easily computationally to compute or to find, but you don't damage the solution that you're looking for because it's order preserving. So another monotonic transformation is logarithm. If we have f of x is log of x, natural log, ln of 1 is less than ln of 3, is less than ln of 7, less than ln of 12. So if we were to ask f of x is equal to ln of x, which one is the biggest, it's still going to be that fourth position, ln of 12. Okay, and so we're going to use natural log because it's going to get rid of this product, which makes it a little bit more difficult to find the best lambda that maximizes this product of the marginal likelihoods. All right, so monotonic transformations preserve the relative ordering of solutions. So we're going to take our joint likelihood, take the natural log, so that means we're going to take the natural log of this superproduct. And so if we do that, well, the natural log of product is the sum of the natural log of the individual factors. So now the superproduct I goes from 1 to n, p of xi, turns into the sum I goes from 1 to n of ln of p of xi. And so now that is the log likelihood, the sum of the log likelihoods. And because natural log is monotonic, the same lambda that maximizes this superproduct is the same lambda that maximizes the sum of the natural log of the likelihoods. And so we select a parameter that maximizes the sum of the log marginal likelihoods. These are called log marginal likelihoods because they're the marginal likelihoods of which we've taken the log. All right. So now, if we do this expression, we now take a look at the probability mass function for the Poisson distribution, and we compute then the log of that probability mass function, the Poisson. Now, of course, if I take that log, that is a minus lambda. That's because we have log of e to the minus lambda. We have plus x ln lambda. That's the natural log of this factor, lambda to the x power. And then we have a minus ln of x factorial. That's the log of 1 over x factorial. So we get minus lambda plus x ln lambda minus ln of x factorial. So now we're going to substitute for this Poisson likelihood, this P of x, and we know what the log of Poisson mass function is. So now we're going to substitute, and now this ln of P of x lambda is now minus lambda plus xi ln of lambda minus ln of xi factorial. So this is going to be our expression that we're going to try to maximize, and it's the lambda value that maximizes this new expression, this transformed expression, is going to be the same lambda that would maximize the original superproduct. And so now what we want to do is find the lambda that maximizes this expression. Okay, so let's continue. And so before we continue on, let's have an interlude in our terminology. This is an optimization problem. We want to find the maximum of something. Now, the something that we find the maximum of, that's called the optimization objective. And that's formally a goal or condition that you're enterprising to reach. Now, in mathematical optimization, it's an expression or function, and you're trying to find some unknown where the function achieves a minimum or maximum. So this expression that we have, that sum, is called the objective function, and the possible values that are unknown that we consider, they're called feasible solutions. And this process of finding the feasible solution is this optimization algorithm. And so here we have our sum of the log marginal likelihood for the Poisson, and it's the sum, I goes from 1 to n, of minus lambda plus xi ln lambda minus ln of xi factorial. And that's going to be our objective. And so from an optimization standpoint, we want to find the lambda, the argument lambda, or argmax lambda, that maximizes the expression between the open and closed curly brace. And we're going to call that lambda hat, and that's going to be our max likelihood estimator, because it maximizes the likelihood of that joint distribution over the data observations. All right. And so, of course, I couldn't be from Massachusetts if I didn't have a John Kennedy reference. So let me play this.
In school, my fellow Americans, ask not what your country can do for you. Ask what you can do for your country.
And so, for the good of your models, ask not what lambda can do for you. Rather, ask what you can do for your lambda. All right. And so I want you to find the lambda that maximizes this expression. And that's our goal. So how exactly are we going to find the maximum of a function? Let's brainstorm about this. Well, one of the things you could do is search sequentially. Another thing you could do is search randomly. And let's see if there's anything else. So let's try sequential search. So we have the domain and range of a function, and we have our x values. Those are feasible solutions. We have f of x. That's our objective, the function that we're trying to maximize. And you start out, let's say that was our function, and you have a low and a high value, and you start searching for that best value among the feasible solutions. So we start out with a first value of lambda, and then we evaluate our objective, and then we remember that our objective, f of x1. Okay. So now we try x2, and we evaluate, and we say, oh, wait a minute, f of x2 is bigger. So that's our new best maximizer, our lambda hat that we're going to remember and hold on to. So then we're going to try x3, x4, and so forth. At some point, we're going to evaluate for some xm where it achieves its maximum. We evaluate f of xm, we say, aha, that one is the biggest. And then we evaluate more and more and more up to including xn, and we find that xn does not improve, so we hold on to xm as that best feasible solution where we achieve the maximum. Now, of course, there's a problem with this. It can take a heck of a long time to do it, And we also have to increment our feasible solution in very small steps. And we don't know if we're going to overshoot, we're going to find the optimizer, the maximum XM, or we're just going to take a really, really long time to find it. It takes too long, and we're not guaranteed to find the maximum. Okay, so let's cross that off. What if we did randomized search? That might work. So let's try that. We have our domain, feasible solutions, and we have our objective, f of x, on the vertical axis, and we randomly try x1. We evaluate our objective. We hang on to that solution. We randomly try x2. We evaluate our objective, and we find that f of x2 is greater. So x2 is going to be our better potential value of lambda, our lambda-hat. And then we try x3. Evaluate that. Maybe it's not better. No, it's not. So we're not going to hang on to that one. We're going to keep x2. And then we randomly try some number of times, n many times. Now, of course, this doesn't have the same issue as the sequential search because it doesn't necessarily take a long time. It can limit the n. But we're not guaranteed how long we're going to search. You could search a really long time and never find it, or search a short amount of time and find the maximum. It can take a very long time if you are probing many, many times randomly, and repeated values are possible, and you might never come close or have enough coverage to find XM, that point where it achieves the maximum, that point where it achieves the maximum right over here, XM. And so there's a problem with randomized search. Okay, well, is there anything else we can do? Let's think about this. We have our function, and let's imagine we have a tangent line. And we slide this tangent line to each point along this function, and we look at its slope. And we slide it. Sometimes the slope increases. Sometimes the slope decreases. Increases, and then it decreases. But if we look at this value, we notice when we reach the maximum, it goes from increasing to decreasing. And if it goes from increasing to decreasing, it has to go through zero in between, zero slope. And so the slope is zero at a maximum or at a turn in the function. And so if we look at this, we have our rise over run, and the slope has to be zero or close to zero in order for it to go from increasing to decreasing. It has to pass through zero. And we have a turn. The slope is zero at that maximum, at the turn. And so how can we calculate this? We can take the derivative, ddx, of our objective function, and we set it to zero and solve for the unknown x, or lambda, since that is our set of feasible solutions or possible values of lambda. So you solve for the unknown after you set the derivative with respect to the unknown to zero for the objective. And so now, again, I ask you, how do you find this lambda? Maximizes this expression. You take the derivative of this expression, dd lambda, lambda is our unknown, and set it equal to zero and solve for lambda. And so this is going to be the form we use for our max likelihood estimation. So we have our dd lambda of the log of this joint distribution over all the observations, set it to zero. So dd lambda of our sum, I goes from 1 to n, of minus lambda plus xi ln lambda minus ln of xi factorial, set that equal to zero. And so the derivative of the sum is the sum of the derivatives. So we bring that derivative inside of that summation, and we get the sum I goes from 1 to n of dd lambda of our expression minus lambda plus xi ln lambda minus ln of xi factorial. All of that equal to zero. So now if we take this derivative, well, dd lambda of minus lambda, that's lambda to the 1 power, that's minus 1. And dd lambda of minus ln of xi, that third term here, is this is our first term, this is our second term, this is our third term. That third term does not involve lambda, so it's a constant. and it goes to 0 when you take the derivative. So we have minus 1 for the first term, we have 0 for the third term, and then the second term, we have xi, which is a constant, it's not lambda, and we have ln of lambda. The derivative of ln of lambda, dd lambda, is 1 over lambda. So we have, for the second term, 1 over lambda times xi is equal to 0. So now, from this expression, we do a little bit of algebra. Well, we have the sum of these minus 1s sub with itself n many times, that's minus n. So we have our leading minus n. And now we have this 1 over lambda xi under that summation. Well, 1 over lambda, that's a constant, so we can bring that out from underneath the summation for that term. And we have 1 upon lambda, the sum I goes from 1 to n of xi. And we have that set equal to 0. Don't forget the equal to 0. So now we're going to take this expression and we're going to do a little bit of algebra. So we're going to add n to both sides of equality, and then we're going to get 1 over lambda is equal to, 1 over lambda, our sum, I goes from 1 to n, xi is equal to n. So we multiply both sides of equality by lambda. That gives us our sum, I goes from 1 to n, xi is equal to n lambda. Divide both sides by n, and that gives us this expression, lambda is equal to 1 over n times the sum, I goes from 1 to n of xi. Now, this expression, we've seen this before. This is just x bar. And this x bar is going to be our estimator that we're going to use as a replacement for lambda. And because it's a replacement for lambda, we write lambda-hat is equal to x bar, and this is our max likelihood estimate. So sometimes in the literature, you'll see lambda-hat MLE is equal to x bar. And that MLE means to note, to tell you how we arrived upon this particular estimator, this reasonable replacement, by using max likelihood estimation. This expression of the likelihood function, the monotonic transformation, the taking of the derivative, setting to 0, and then the solving for lambda. Okay. And so when you're estimating a Poisson distribution from observations using max likelihood estimation, the best lambda value that you can choose, or replacement, or estimator, is not by sequential search, not by random search. Rather, it's x bar because it maximizes the likelihood function over all observations by solving for when the gradient or the slope or the derivative is equal to 0. That's the turning point where we reach the maximum in the objective function. And so, again, we call it lambda-hat MLE because it's the max likelihood estimate. And it's the procedure, that note in the notation, about how you arrived upon this particular estimator or reasonable replacement for lambda. And you do this with each parameter for your distribution. If we had a gamma distribution, we would have an alpha MLE, and we'd have a lambda MLE for that gamma. And it's the same procedure. And so this procedure of setting the derivative of the likelihood function equal to 0 is done for each parameter. And that's in contrast to method of moments estimation. This is max likelihood estimation. Okay, and so with that, that's all I have. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.